Hey all, editing me here. I just wanted to pop in and say hi, long time no see, but also a lot of this work that I'm doing in this video is based off of my literature review, which is on cosmic neutrino sources. It's still being marked right now, so I haven't been able to upload it online yet, but when I do, I'll pop a link into the description with it, and that also includes all of my references that I've used for the literature review and whatnot. But in the meantime, while I'm waiting for it to be marked and for the feedback to come back, I'll list a couple really key references that I've used to inform just the review itself and also the video too, so hopefully those will be sufficient for the meantime. Hey guys, welcome back, long time no see. I think it's been, what, 3-4 months now since I last posted, and I'm really sorry about that. The reason I've been away is because I've been quite busy doing a literature review for the 4th year of my Masters in Astrophysics, and that's actually going to be the topic of today as well. So for my literature review, one of the main things I was researching was cosmic neutrinos and essentially how we detect them and what we think, or where we think they're from, essentially. So I don't know how much everybody knows about neutrinos. They can be quite a mysterious particle in general, so I'm going to try and bring everybody up to date with some of the basic knowledge. So neutrinos are very lightweight and they're neutrally charged, so chargeless particles, a bit like the neutron, which is why they're called the neutrino, essentially. Regarding their mass, we don't actually know how much they weigh, but we do know that in kilograms, they probably at most are around 10 orders of magnitude lighter than the proton, which is about 10 to the minus 27 kilograms, meaning the neutrino is probably at biggest 10 to the minus 37 kilograms. Which is an extraordinarily small amount. I mean, it's no wonder we thought that they were massless for a long time. We know that there are 3 flavours at least corresponding to the 3 leptonic generations. So we've got the electron and the electron neutrino, the muon and the mu neutrino, and the tauon and the tau neutrino. Sometimes some people call the tauon the tau. Both are fine. I use the word tauon personally. From a more astrophysics point of view, the neutrino detectors that we have on Earth detect a surprisingly large amount of ultra-high energy neutrinos. So these are typically in orders of TeV to PeV, so that's up to 10 to the 18 electron volts, which is quite a huge amount. For reference, the 3 sources that we know pretty well regarding neutrino creation, so the Sun, the Earth, and I believe nuclear reactors, they can account for, neutrinos up to the orders of 10 to the 6, so mega electron volts, possibly even giga electron volts, maybe. So there's quite a huge gap in energy that, all of these, they don't really explain these ultra high energy ones that go up to 10 to the 18 or possibly even 10 to the 20 electron volts. So we know that they're of cosmic origin, we just don't really know what's going on, and we can't explain them with things that we know that are close to us, such as the Earth and the Sun. So they're quite mysterious in general. Another cool thing about neutrinos, it's also an annoying thing, is that because of their lightweight and their neutrally charged nature, they almost never interact with anything. So that's a good thing in that from their site of creation, however many billions of parsecs away up to their detection on Earth, it's almost guaranteed that they haven't been affected by anything in between, so like any intermediate medium such as the intracluster medium. And that's good because it means that, there's nothing that we need to really account for, such as dust extinction, which can really affect results, especially when we're talking about observing in blue or ultraviolet light. So they don't have that problem. This can also bite us back in a way because, if they don't interact with anything, how are they going to interact with, the detector? How are we going to detect them if they're so sort of inactive in a way? And so it is quite hard to detect neutrinos, but it is possible, and we do have quite a lot of neutrino detectors that are doing a pretty good job at detecting them albeit indirectly. And one of these detectors is the ice cube neutrino detector in the Antarctic. So I'm just going to call it ice cube from now on, but you know I'm referencing the ice cube neutrino detector. Ice cube covers about 1 kilometer squared of surface area on the Antarctic surface, and it's pretty much right next to the South Pole if I remember correctly. It goes about 2.8 kilometers down into the ice, which is a remarkably huge amount. And so volumetrically I think it's just under 3 kilometers cubed. It has around 5,000 detectors if I remember correctly, and these are all suspended on strings inside the ice. And so the main goal of Ice Cube is really to just figure out these cosmic sources, and also just to understand the nature of these ultra high, TeV to PeV neutrinos that we're detecting. The main way that Ice Cube and quite a lot of detectors in the world as of now, I think, detects neutrinos is through Cherenkov radiation. And so this is where something like a really high energy neutrino is going to hit the ice, in the case of Ice Cube, and it's going to undergo something called a W exchange or a charge current interaction. So for example, it will hit a neutron, and as a result of that collision it will produce a proton plus a lepton of the same flavour, but not the neutrino version. I don't know what you call the non-neutrino leptons. But for example, a mu neutrino will hit a neutron, produce a proton plus a muon rather than a mu neutrino. And so it's actually this muon, or this electron or tauon, that we can then detect, essentially. So let's continue on with the muon example. So if this parent mu neutrino is going at relativistic speeds, in which it probably is, and it undergoes the W exchange, this resulting muon's just gonna carry on. It's gonna have a lot of that energy, and in particular a lot of the momentum from the parent neutrino. And so if this resulting muon is traveling faster than the speed of light in the medium, so for ice it's 75% the speed of light, it will emit something called a Cherenkov cone, or Cherenkov light. You can also see these in nuclear reactors as well. It's this really beautiful blue light when you turn the reactor on. What's really great about Cherenkov radiation as a method of detecting neutrinos, indirectly of course, is that it does preserve a lot of key information from the parent neutrino. So to some extent you can recover the energy of the neutrino, the rough location or whereabouts as to where it came from, and to some extent as well you can also figure out the flavour of the neutrino, and this is actually quite important as well. So in the case of a muon, or the mu neutrino for example, it will undergo W exchange and produce one muon. This one muon will create a track down the detector, and it will also create one cone. So nice and simple, one track, one cone, detector sees one thing, nice, great. Whereas with an electron neutrino, it will actually create essentially like an electron shower, because you've got a lot of electrons in the ice as well. And so you get multiple cones from the electron itself, and so you get a more fuzzy looking ring on the detector. And to some extent you can sort of figure out what's an electron and what's a muon, although there's a lot of nuance and sort of haze between the two. It's not exactly a perfect science, let's just say that. Tau neutrinos and tauons are a much bigger problem. In fact, it's almost impossible to detect them, and this is mainly because the tauon has a very short lifespan, about 2 × 10⁻13 seconds to one significant figure. And this is a problem because this resulting tauon will produce a Cherenkov cone, but it will also decay into something like a muon, which will then produce another cone. But this should be a good signature that a tau neutrino has interacted, but because the tauon decays so quickly, these cones tend to be quite close together, and so the detectors can't really resolve this sort of double cascade, if you will. So I've pretty much explained what neutrinos are to a very basic level, and also how we can detect them using Cherenkov radiation. So let's actually talk about 2 of the main sources that we think are sites of ultra high energy neutrino creation. in outer space, and that is active galactic nuclei, or AGN, and also gamma ray bursts, or GRBs for short. So let's start off with our strongest object, and that is active galactic nuclei. I'm just going to call them AGN from now on. These are very early universe galaxies. I think their redshift the number density peaks at a redshift of around 2, if I remember correctly, and it slowly declines as you get closer and closer to the current time. So, you know, they're very early universe galaxies, and in general, understanding them better will help us understand the early universe better, and we don't really know that much about the early universe as well, so they're really important objects that we need to, just observe further. So, as an example, quasars, Seyfert galaxies, quasi-stellar objects, or QSOs, or blazars, these are all different types of AGN. And what makes an AGN different to just a regular galaxy is that their centers, so the nucleus, the active galactic nuclei, is producing extreme amounts of power, so luminosity, and in the case of quasars and blazars, this overpowers the host galaxy itself, so the stars around it essentially just, you can't see them because the actual nucleus itself is so powerful. And this is why we used to accidentally think that they were stars at one point, because, their centers are so bright they just look like stars to us. But we figured out from looking at their spectra that they don't look anything at all like stars, and they're clearly something else entirely. So when it comes to neutrino creation, we believe that there are 2 main core components of the AGN that are important to neutrino creation. We've got the accretion disk, which surrounds the supermassive black hole, and then we've also, if there are any, we also have the relativistic jets, which are sometimes produced from the accretion disk and black hole. So the accretion disk itself is a very highly magnetized region of a galaxy, and so you can get a lot of acceleration via synchrotron processes, and this is essentially where you accelerate charged particles such as the proton, for example. And so what we believe is the main cause of ultra-high energy neutrino production is that these protons are being accelerated via these synchrotron processes to relativistic speeds. They interact with the background photon, and what happens is that the proton then collides with the photon and produces something called a delta plus resonance, or a delta plus particle. And this will then decay into pions, which will in some channels decay into neutrinos and leptons of the same flavour. Some people also suggest that kaon decay is also responsible for some neutrino production, but they're just both ideas. Now, what's great about AGN is that we actually do have some evidence of some AGN potentially being sources of high energy neutrinos as detected by IceCube. Our main one is in fact an AGN called TXS 0506 plus 056. I will just call it TXS from now on because that is a mouthful. What happened was there was a neutrino event it was either 2014 or 2015 or 2017, where we detected a really high energy neutrino event using IceCube, and we were able to locate it pretty close to the AGN itself. It was, I think the separation was about 0.28 degrees, which is actually quite a huge amount, but it was the closest AGN by far, and I don't think there were any other events that were nearby that could have explained it. Plus, I believe it did coincide with a gamma ray flare from the AGN as well, lending it some more credibility. So that's some pretty good evidence towards, one specific AGN being a neutrino source, but, that's pretty good. We also have NGC 1068. A lot of people also call this Messier 77. This also had a respective neutrino event traced back to very close to the AGN center as well, and also NGC 4151, which a lot of people colloquially refer to it as the Eye of Sauron galaxy because it definitely looks like the Eye of Sauron, and it is a really beautiful galaxy in general. So next up we also have gamma ray bursts, and we don't really know that much about gamma ray bursts, but in the most vague sense possible, They are violent explosions that you can see all throughout radio waves up to gamma rays, hence their name, gamma ray bursts. It's very hard to classify because we don't know a lot about them and they're quite hard to observe. But one thing that's quite interesting is that if you plot their distribution on a frequency graph, so you plot how many of them have a duration of like half a second, 1 second, whatnot, you can actually see a pretty nice bimodal distribution where you've got some short gamma ray bursts and some long ones, and so we tend to classify them as such. So we have the two main types, the short gamma ray bursts, or short GRBs, and these are typically associated with binary neutron star mergers, or sometimes a neutron star black hole merger. And we also have the long duration gamma ray bursts, which are commonly associated with core collapse supernova. So this is where you have an extremely massive star, so 40 solar masses for example, collapses down, and in a very violent explosion it scatters everything. You get a lot of heavy element production and some other processes that go on, and also potentially some neutrino creation as well. When it comes to the actual mechanics, let's say, of gamma ray burst formation, we don't know that much. So if you want to go one step further and talk about, well, how are neutrinos specifically made in gamma ray bursts, well, you're left with more questions than you have answers, unfortunately. One of the main theories that we have as to how GRBs are, made, essentially, is the fireball method. So in this case, it's quite hard to sort of explain. There are a lot of aspects to it, but what we need to know is that when something very large collapses, it's going to produce quite a lot of shocks, and these shock fronts, they interact and they thus accelerate the particles, such as, the proton, up to relativistic speeds. So essentially you get a lot of collisional shock fronts that, not only do they produce a lot of the gamma rays themselves, but they also accelerate a lot of the matter out to relativistic speeds and just to great distances in general. There are some arguments against it, so in some papers they've also argued that actually the gamma ray burst production has to be a lot more magnetically dominated, just by how the light curves are shaped. So for example, some may argue for a more pointing flux dominated jet model, where you've got a lot more, because of the magnetism? Yeah, that's the correct word. Because the star itself, or the merger itself, is going to be a very magnetic environment, you should expect a lot of the gamma rays and like the electromagnetic waves themselves to be produced via some method through that theory as well. But some people have also argued that actually it could be a mix of both as well. We just don't really know. And one thing that's interesting that I personally found with my research is that a lot of gamma ray burst light curves are very unique, and they're all different. They're like snowflakes essentially, no two of them are the same. So it could actually be that this sort of thermal fireball and this, this magnetic pointing flux thing, it could be to different proportions, unique to each gamma ray burst, but I don't really know. I'm not the gamma ray burst expert, I'm just here to learn about neutrinos. So when it comes to specifically neutrino production, well, if we know that we're getting, there must be some sort of acceleration of matter going on with these gamma ray bursts, and that's somehow linked to the gamma rays themselves, well, you could argue that since they're being accelerated to extremely high speeds, that, we've got something very similar to the photohadronic processes that we talked about with the AGN before. So you've got very, fast moving protons interact with photons, make delta pluses or kaons, decays into pions, decays into neutrinos, that kind of stuff. But apart from that, I haven't actually found any other sort of method for neutrino production apart from maybe the leptonic processes, which could actually have some bigger contribution here. We just don't really know. When it comes to the evidence for gamma ray bursts and cosmic ultra high energy neutrinos, we don't really have any, unfortunately. That's mainly because it's likely that our detectors just aren't sensitive enough to, detect them. That leaves you thinking with the question, well, why do we think that gamma ray bursts might have some connection or association with these ultra high energy neutrinos in the first place then? Well, mainly because given the somewhat limited theories that we have, they should be producing some high energy, very highly relativistic, particles like baryons, and hence, theoretically some high energy neutrinos should be made, but we also have some other things that also lend some credibility to the GRB, neutrino theory, if you will. We do know that supernovae in general, just regular ones, produce neutrinos, and we know that the majority of the energy of a supernova explosion is carried away in the neutrinos. One key case study for this was actually supernova 1987A. We detected quite a lot of neutrinos from that event. I think it was above 20 individual neutrinos, which I know that doesn't sound like a lot, but for neutrinos this is a huge amount, especially just from one source itself. And so this supernova actually confirmed the idea that neutrinos were produced in supernovae. And so there's no reason to think that, well, gamma ray bursts from supernovae, so long duration ones, shouldn't produce neutrinos. They absolutely should. When it comes to short duration gamma ray bursts, so the things like the binary neutron star mergers, there's much less evidence towards, what's going on with them specifically, and that's mainly because mergers themselves are extremely rare, especially the neutron star ones. And when it comes to things like black hole mergers, so binary black hole mergers, they do occur a lot more frequently than neutron star ones, but unfortunately they don't really produce any electromagnetic light, so we don't get any gamma ray bursts from them at all, so they're quite hard to detect apart from maybe the gravitational waves. However, that leads us on to our next point, in that we do know that neutron star mergers should be producing gravitational waves. We actually saw this in the case of, I'm going to try and remember this name, GW170817, I think? Yes, that was in 2017, I think. And this was a neutron star merger which not only had gravitational waves, which we detected with LIGO Livingston and LIGO in general, but we also were able to detect a subsequent gamma ray burst, I think. So that was really great in tying gravitational waves to gamma ray bursts to neutron star mergers. So we know that mergers themselves are multi-messenger events. We know that they produce light and they also produce gravitational waves. So it's kind of odd that it would favour those two but not neutrinos, if you will. It's a bit of a sort of a straw man argument I'm giving, but I mean, technically it works. So when it comes to neutrino detection just in general, one thing that's quite exciting that people should definitely look forward to in the next decade is the upgrades to the IceCube neutrino detector, which they're calling IceCube Gen 2. And so what they're basically going to be trying to do is expand, I guess, the observing capability of IceCube itself and just neutrino detection in general, with the main goal of being able to find these cosmic sources and to, better understand them just in general. The way that they're going to be doing this is by physically expanding the detector itself. So while the volume right now I think is just under 3 kilometers cubed, they're going to be expanding that up to 7.8 kilometers cubed, which is a huge upgrade. But yeah, they're basically going to be expanding it by a huge amount, and this means they're going to be adding, I think, about 12,000 more detectors in the ice. So these are the individual detectors themselves. And they're also going to be including an optical and a radio array, and this I think is mostly for being able to detect Cherenkov radiation better, to be able to, to observe it better and to get better calibration techniques, I guess, for, future data, essentially. And in general, I think what all of these upgrades are going to do is increase the sensitivity by, I think, about 5 times. It's also going to hopefully be able to give us better resolution, especially when it comes to locating the sources themselves. And also a bigger detector means you're going to be able to catch more neutrinos. You've got a better chance of just collecting just more neutrino data, which is just which is just good in general. And not only that, the expansion of the detector itself and having the strings just, more of them, means that we should be able to expand the observed energy range up to 10 to the 20 electron volts. So I think that's around just under an eta electron volt. So conclusions: neutrinos are very lightweight. They are annoying to detect, but they are also very key to understanding high energy events in the universe, such as in the centers of AGN and GRBs and other things that we just don't know about. We're able to detect them indirectly through Cherenkov radiation because we can't detect them directly. And so what's important about Cherenkov radiation is that it preserves the energy, the direction, and the flavor to some extent. But it just recovers it just gives us a lot of key information about the original source of the neutrinos themselves. It's just being able to tap into that information is what we're trying to do right now. We know that AGN are most likely a source of cosmic neutrinos. We have 3 AGN in particular that are likely sources of neutrinos, plus a couple others that I haven't really listed, mainly because they've sort of been at the heart of maybe 1 or 2 studies, but they haven't been, extensively analysed, and there's not much data surrounding them, or they just have a very insignificant event. Well, not an insignificant event, but an event of some significance, but not a lot. So we know that they're most likely a source of most of the cosmic neutrinos that we detect. GRBs probably not as much, and we don't have any evidence towards them, but there are some sort of underlying theories as to why they should be producing neutrinos. The upgrades to IceCube, so IceCube Gen 2, means that more neutrinos will be detected, more neutrinos at higher energies will be detected, and we should also be able to have, more sensitive equipment and just generally better data in general. Anyway, so that basically concludes my literature review. I hope you found that interesting, because I certainly did. One of my favourite aspects of the review was actually the tau neutrinos, because I don't know why, I just found them really interesting, and why we don't see them as well. What's going on with that? Why can't we detect them? What's their signatures that we're missing out on, essentially? And I just found that really interesting. I also found the AGN part of the literature review very interesting, because I've studied AGN before in class, and also as part of research projects, so determining the masses of the supermassive black holes inside them as well, and I just find them really interesting. I find them really interesting, and also fairly mysterious as well. But yeah, so that concludes my video. I hope you really enjoyed it. I will be back very soon with probably some more fun crafty stuff, because my birthday is coming up soon and I need to bake a spacey cake. So stick around for that, and I'll see you soon.